So I would like to thank the organizers for inviting me to speak. I was trained in automorphic forms in the Langland's program, and I had some various results in this field. I think it's an amazingly interesting field. But at some point, I met Igor Sparlinski, and I really enjoyed the style of math that he did, and so started doing exponential sums. And my talk is a sort of work that's roughly been inspired by work that I've done with Igor. It's all the results that I'll show, the ones that I was involved in, probably would never have happened if I hadn't met Igor. So it's been a pleasure to work with him over the years. I'm a little nervous, but once I get rolling, I'll be okay. So, happy birthday. So one of the topics that I've been involved in, we looked at this a little in the special session yesterday, are Beatty sequences. Beatty sequences are generalized arithmetic progressions where you take, two real numbers, alpha, beta. Alpha is generally taken to be something bigger than 1, but not necessarily. They're interesting if you assume that alpha is irrational. You get an interesting sequence of integers by taking alpha times n plus beta, throwing away the decimal and taking the integer part of that. And you can consider questions about these sets of integers. For instance, it's interesting to look at the primes that fall into this kind of a sequence. The sequence itself hits like every arithmetic progression that's possible. And a lot of results are known about such primes. This is an old result that goes way back, probably to Vinogradov. If alpha is irrational, then the prime counting function pi alpha beta x, which counts the number of primes up to x, which have this form, so prime numbers in the Beatty sequence, satisfies an expected asymptotic formula. I wanted to just make a remark. My talk doesn't have proofs. It's mostly a collection of results, but I wanted to just say a few things about Beatty sequences. So let's say we take beta equal to 0, and the question is, how can you recognize when an integer m belongs to this kind of a sequence? So if alpha is irrational, then let's say alpha is greater than 1 and it's irrational, and we put gamma equal to 1 over alpha, then you can simply notice that if m is the 4 of n times alpha, m will be less than, it's strictly less than n times alpha, and it's strictly bigger than n alpha minus 1. So dividing by alpha, you get n minus gamma is less than gamma m, less than n. This part you can write as the 4 of gamma m plus the fractional part. And so then you get some inequalities for the fractional part of alpha m. This should be less than n minus the 4 of gamma m. It should be bigger than n minus the 4 of gamma n minus gamma. But the fractional part always lies between 0 and 1, so this tells you that this integer has to be 1, and this is 1 minus gamma. And so the condition that m lies in this Beatty sequence is equivalent to saying that the fractional part of alpha m lies inside the open interval from 1 minus gamma to 1. And so this condition, the fractional part is a periodic function, so you can, similarly this is saying that alpha times m, gamma times m can be written as some integer translate of this interval. So the characteristic function of this set is a periodic function with period 1. It has a Fourier expansion. You can take the characteristic function, smooth it a bit, and approximate it by a trigonometric polynomial. You get some loss. Then using the trigonometric polynomial, you can, the constant term of the trigonometric polynomial will be gamma, and then the rest you have a finite collection of exponential functions. So if you can get decent bounds for the exponential sums that arise, and relate it to the error term that's introduced in the smoothing, then you can get information, about how many primes lie in this set. Okay, so one of the problems we worked on was this problem of, we looked at exponential sums where we take n running through set arithmetic progression a mod q. The von Mangold function detects primes, and then we multiply by e to the 2 pi I gamma kn, where in this case gamma is an irrational number of finite type. And we show that such sums can be bounded with a power of x savings in quite a long range, with the integer k varying up to a power of x, and even the modulus q varying up to a power of x.
What do you mean by the type?
The type is just a measure of how closely you can approximate the irrational number by rational numbers. So, I don't want to give the wrong definition, so I'll give you a definition after my lecture. Most, any algebraic irrational is of type 1, and almost all real numbers are of type 1 in the sense of Lebesgue measure. But certain numbers, like Liouville numbers, are infinite type, so those are the ones that you need to avoid in some applications. Although I'll mention that this asymptotic holds regardless of the type, but the type often determines how quickly these types of approximations will converge. So it's actually the finiteness of the type that gives us this exponential savings in the exponential sum. Okay, then we use that previous result to study, primes in the Beatty sequence. So here we're basically looking at primes that lie in the Beatty sequence. If you neglect the lower order terms, this is counting, is giving a weighted count of the number of primes in the Beatty sequence, which lie in the progression a mod q. And we basically get the expected number, alpha, so alpha to the minus 1 times the number of primes up to ax plus b, alpha x plus beta that lie in the same progression, plus an error term that has like a savings of x. So it's a surprisingly close estimate, at least for irrationals of a finite type.
So excuse me, kappa can depend on the type of it?
The kappa only depends on the alpha and the beta.
Depends.
Yeah. This constant kappa depends on, it really just depends on the alpha. Okay, this talk is sort of like half, well, I wanted to mention this result. It's, I don't know how much that's inspired by what we did, but it's very related to the kinds of questions that we look at. I thought this was like one of the nice results that I saw while working with Igor in this area. So it says that they showed that for almost all irrational alpha, you can get this, you can show that you get a sort of a lower bound on the number of primes for which both p and alpha p plus beta 4 are both primes. So it's somehow like a step toward some kind of a k-tuple conjecture. But it only, this bound holds for almost all alpha. It's an example of one of these results where we know it's true for almost all alpha, but we don't know any particular alpha for which it holds. This was a result we did an analog of the Vinogradov 3 prime theorem. We showed that if you take the collection of, if alpha is irrational of a finite type, then you can take the collection of primes that lie in the Beatty sequence, and you get like an analog of, the Vinogradov 3 prime theorem. So that if you have, as long as this integer k is larger than alpha, you can express every sufficiently large number with the same parity as k as the sum of k primes from the Beatty sequence. And you get almost all even numbers. So again, this is basically boils down to showing that the exponential sums that you use to estimate the various the minor and major arcs in the circle method, that those estimates are sharp enough that you can get this kind of result. We don't have one. We didn't give one.
Depends on.
Yeah, it would depend on the alpha, but we didn't actually try to go that far with it. So it's a good question.
Maybe you can by essential digit with a small number and they can put for all numbers.
I think in principle it could be done for like a given alpha, but I don't see any like particular obstacle to it. But the lower bound would have to be, I don't think numerically you could say that this would work, give a lower bound that was valid for all alpha. It would depend on the alpha, but there should be some effective lower bound that can be given in terms of alpha. This was a different kind of project that I worked on that was related to, well, this came out of some other stuff which I'll talk about later, but here I was considering a zeta function. I look at a slightly different set here, p star alpha beta. These are primes, p sub n. If you index the primes, or you denote the nth prime number as p sub n, then here we're looking at primes for which the index lies in the Beatty, in the set of the Beatty sequence. And you form a sort of a partial zeta function by just taking a product only over the primes in the set. But then here we have the usual Euler factor, but then that Euler factor is raised to the power alpha. So this product is only over a multiple of, or a set of primes which has density 1 over alpha. If alpha is large and irrational, then you're looking at a set of primes which is density 1 over alpha, but then the Euler, local factor for the Euler product is raised to the power alpha, so it's similar to the actual zeta function. And I showed that this function, if defined this way, is Pretty much just the same as the zeta function times the exponent of some reasonably nice function which is analytic in this region, sigma bigger than 0. So you can form, you can say that the Riemann hypothesis is true if and only if this Beatty zeta function has no zeros except for those on the half line. Huh?
I mean, you just choose the points in the sequence.
Doesn't work as nicely. You can do that, but you don't get these. You wouldn't get. You would get the same if the alpha is irrational. You can get a similar statement, but it would not hold for all sigma bigger than 0, but rather for all sigma bigger than some number, which would be maybe close to 1. So you can do a little bit. You can say something about like the zero-free region. And that's something, I think I did this in my paper, but no, and it's a little bit different. It's a good, that's a good question, but it wasn't covered by my method. I think maybe all I did was comment on it. One thing about this, it shows you that, for instance, if you just take, a set of primes where you're just taking, 1 out of every billion primes or something, form the zeta function out of those, raise the factors to 1 billion, then you essentially recover the analytic information about the zeta function that we care about inside the critical strip. So it shows you that, for instance, the truth of the Riemann hypothesis can never be give you enough information to say what's happening about primes which are neighbors to one another. Because here I'm just ignoring primes which are not associated to each other inside the Beatty sequence. This is a kind of similar area that I looked at, was studying primes in the Piatetsky-Shapiro sequences. So Piatetsky-Shapiro noticed that we know everything about primes that are represented by linear forms, but we don't know anything about primes which are represented by polynomials of degree 2 or more. So he tried to study a thin set of integers which are somewhere between linear functions and quadratic. And he showed that if you take any number c up to from 1 up to 12 over 11, you can still show that there are infinitely many primes of this form, and you get an asymptotic formula for that. This result has been improved. I think the current record is at 243 over 205. May have that. Yeah. Okay. This is on. So this is a work of Rivan Wu. Okay, here again you can use exponential sum techniques like van der Korpit's method and exponent pairs to study questions for such sequences. In this paper with myself, Roger Baker, Jörg Brudern, Igor Sperlinski, and Andreas Weingartner, we studied various questions related to the sequence. So we estimated how many integers n up to x for which n to the c is square free. This had been done before, but we got a sharper, like a larger range for c. One thing that we studied was the largest prime factor of the floor of n to the c. And we showed that for any number c in this range, we can say that the largest prime factor of n to the c is less than or equal to n to the epsilon, and that holds for a set of integers, at least size x to the 1 minus epsilon. So there, one can find integers of this form which have reasonably small prime factors or many prime factors. Going the other way, we showed that there's a positive function theta of c for which you can find, sequence of integers for which the largest prime factor of n to the c is at least this large. And this works for any integer c as long as it's non-integral. We have sort of, we have bounds for c close to 1 and also bounds for as c goes off to infinity.
So this theta of c, how big is it?
Huh?
Theta of c?
It depends on, it depends on how close c is to 1. So I think that, I forget what we got like for c close to 1. Yeah, it's like piecewise linear. As c goes to infinity, it's something like some constant over c squared. For c close to 1, it's some piecewise linear function. Here's like another result we did in this paper. I guess one of my the subjects I kind of like is Carmichael numbers. So a Carmichael number is a composite number that satisfies Fermat's little theorem. A to the n is congruent to a mod n for all integers a. And this it wasn't known until '94 that there are infinitely many such numbers. In our result, we showed that for any c in the range from 1 to 147 over 145, there are infinitely many Carmichael numbers which are composed of primes from the Piatetsky-Shapiro sequence. I also I have a similar result like this for Beatty primes as well. Like something we did more recently was to consider sequences where instead of taking all integers n, considering floor of n to the c, we were restricting the values of n and seeing what we could say. So here, if we call a P sub r the set of r almost primes, we showed that for any fixed c up to 77 over 76, the number of integers n in x which are p8, so 8 prime factors or less, and for which the floor of n to the c is prime, is at least x over log squared. So we generate prime numbers from almost primes using this Piatetsky-Shapiro function. We also looked at the other question, which is, can we generate almost primes from prime numbers? And so we have various results in this direction. So I guess if c is close enough to 1, it's enough to take, again, 8. You can find infinitely many primes for which the floor of p to the c is p8, has at most 8 prime factors. The techniques are a little bit similar, but they're also sort of different. There are very few results known about integers of this form, p to the c, floor of p to the c. In fact, I think in previous times, Balog had studied this, but for values of c less than 1. And even in that range, there are open questions. But in that case, counting primes has to do with saying something about gaps, unconditional gaps between primes. And our result for almost primes also extends to all large values of c. Okay, something my student worked on at some point was to show that if you have a Beatty sequence and the Piasecki-Shapiro sequence, and you look at the intersection of the two sequences, that the intersection contains infinitely many primes, and it contains asymptotically the same number of primes that you would expect as long as the various parameters are in these ranges. So, C can go up to 14 over 13. He also assumed that alpha is irrational of finite type. I should mention, that the assumption of finite type can often be removed in most of these results. The Vinogradov theorem I mentioned before was proved, to hold for all alpha. I think this was a result of Bob Vaughan, and it takes additional effort, different kinds of tools. Usually I try to avoid that, but you have to know your own limitations, I think. Okay, recently I started looking at these, I was kind of interested by these questions of, what can we say, if anything, about, collections of primes where you just take one out of every 100 primes, you form that collection. What can we say? And I'll leave it to this audience to say more. I think it's interesting that we can say anything, but some recent theorems have actually lend themselves to this kind of a study. This generalizes one of the results I had on the board before. I looked at this class of sets. These are classes of primes P for which the counting function is close to, extremely close to some multiple of pi of x. So the number of primes up to x in the set P should be a fixed multiple of pi of x plus an error term that's not too bad. Sigma 0 plus some function epsilon, where epsilon satisfies this. And depending on how small you can make the sigma 0 tells you something more about how far you can go with this. And I also looked at a different class, another class which satisfied the stronger estimate. Pi of p of x is a delta pi of x plus this small error term. But this kind of these kind of sets are natural. If you're just taking every 100th prime, then you get, in this case, you would get delta equals 1 over 100, and this would actually be big O of 1 in that case. So for any of these types of sets, I proved an analog of this theorem on the zeta function, so that you can take this function zeta p of s. You define it by letting the primes just run over your set P, and then to get things to work out analytically, you need to take these Euler factors and raise them to the power 1 over delta. And if you do that, you get a function which agrees with the zeta function up to some nice factor in the half plane sigma bigger than sigma 0. Another thing I did in this paper was to say, I did a sort of additive result, which is if you have a set P which contains the prime 2, and it sits in the set B of delta E, B of delta epsilon, then this is an exact additive basis for the integers. So you can find an integer h such that the h-fold subset contains all natural numbers except some finite number. An earlier results of Sarkozy showed that you could show that any such set like this was an asymptotic basis, but not necessarily exact. And to get the exactness, I used a theorem of Shu, which said that if you have any arithmetic progression, you can find a string of consecutive primes, which that all lie in that fixed arithmetic progression. So, for example, if you take the set which consists of 2 and then every 100th prime after that, every sufficiently large natural number can be written as a sort of, as h copies of numbers from this set. I didn't actually figure out what h works in this case, but...
So you said, you're talking about the every 100 prime, right? That's what, we're saying that. But your definition was, earlier, was using the prime counting function and comparing that with pi of x over 100.
Yeah.
This is slightly different because, it depends on the gaps between consecutive primes, right?
No, because I'm the number of primes up to a given number x wouldn't.
It changes
As x increases, the primes start filtering down. You could go a long way before the next prime appears, but it's more a question of, as the primes appear, 1 out of every 100 of them always go into this one slot, and then you fill up the other slots like this, and then you come back. So I'm not, let's see, in this bound I'm not comparing pi p of x to li of x, but rather to pi of x. So I'm getting like a fraction of the actual number of primes. Okay. Okay, well. So some other stuff that I've done, working with L functions, I studied questions about, characters and this is like a result of a different flavor, but we define the usual Legendre symbol, and if I define n1 of p to be the smallest natural number, which is a non-residue, there are various results are known on this function. So Gauss showed that n1 of p is never more than 2 root p plus 1 if p is congruent to 1 mod 8. I think this was the first result in this direction. Vinogradov showed that n1 of p is no more than p to the kappa for any kappa exceeding 1 over 2 root e. And then Burgess, I think using the Riemann hypothesis for curves, I think he was able to show that, or using the Weil-bound, he was able to show that n1 of p is no more than p to the kappa for any kappa bigger than 1 over 4 root e. This bound of Burgess has stood since 1957. I think this was I think Eager was like 1 year old in this year. The Vinogradov conjecture is that the first non-residue occurs by the time you get to p to the epsilon. And if you assume like the extended Riemann hypothesis, you can do better. So under the ERH, the Vinogradov conjecture is true, and Ankeny showed that it holds in a stronger form, n1 of p is never more than log p squared. One of the things that Heath Brown looked at the question of whether the Burgess bound could be tight, so whether p to the 1 over 4 root e is the best you can do on this problem. And he showed, so he said, suppose that the first non-residue is at least p to the 1 over 4 root e for infinitely many primes. You take roots to the certain function h of z, and for every root of this function, you can find a sequence of numbers tending to 1 such that ls sub p, the L function associated to the Legendre symbol is 0 for all primes p in the set, and s of p minus 1 times log p tends to this number minus 4z. So you get a sequence of zeros of these L functions which tend to 1. In other words, if the Burgess bound is tight, then it implies L functions close to 1. The extended Riemann hypothesis rules out such zeros, but there are other ways to rule them out in particular cases. this would tell you, for instance, that the number of counterexamples to the number of primes satisfying this kind of bound, there can't be too many of them. But yeah, so with one of my colleagues, we looked at generalization of Heath-Brown's theorem. And so in our setup, you have like two real numbers, kappa and lambda. Lambda is at most a quarter, kappa is less than lambda, and our assumption, well, if we take the counting function of non-residues up to x, we assume first off that n1 of p, the smallest non-residue, is at least p to the kappa. So we're assuming that Vinogradov's conjecture fails with this exponent kappa, and that the density of non-residues looks like delta of theta plus little of 1 times p to the theta for some function delta which has this kind of a shape. So it's going to start out at 0, kind of meander its way up to a half, and then continue at a half after that. And it does. Our assumption is it does so along some twice differentiable path, or I guess triply differentiable. So we assume that this delta you get by integrating some probability distribution which is supported on kappa lambda. In the case where kappa is 1 over 4 root e and lambda is equal to 1/4, this kind of assumption is forced on you. So Heath-Brown's result actually follows as a special case of this consideration. And then we showed that in this situation, if you have any solution to the Fourier transform of d at k is equal to 1, then you get infinitely many primes in a sequence S, which gives you zeros of these L functions, and S is approaching 1, but S minus 1 times log p approaches this fixed number. So you get a sequence of zeros of the L function, and you know sort of where they are. This would, for instance, this would allow you to take, say, a certain neighborhood of some point. If you could just show that the L functions were never vanishing in this little small pinpointed neighborhood, that would imply that the Burgess bound can be broken. So that 1 over 4 root e isn't the best you can do. Okay, well, I'm a little out of time, so let's see. I'm out of time, right? Okay, so let's see. Density of residues. I'll mention this result I had recently with my student where, well, we weren't able, the Burgess bound says p to the 1 over 4 root e plus epsilon. We did what we could to get rid of the epsilon, so we replaced p to the epsilon by an explicit function of p, which is x of the square root of log p double log times e to the minus 1. So this is what the p of the epsilon is in Burgess's theorem, and we also showed that this bound is good for the kth non-residue as long as k doesn't exceed this number. So you get a whole sequence of non-residues below that bound. And we use ideas from Granville and Sander-Arjen. Well, the other thing I was hoping to say just at the end is, like in recent work, I've been working with Igor on character sums, where we study character sums, the chi mod q, where q is a large power of a fixed prime p. We hope our results in principle should extend to other types of moduli for which the kernel is small. And we get stronger estimates for short character sums, a wider zero-free region for LS chi, and bounds for the absolute value of LS chi when chi is S is close to 1. So one of the results that came out of this is that we showed that the value of L1 chi, if chi runs through characters in the sequence, so fixing p but letting gamma tend to infinity and taking characters in this sequence, you can get this bound on L1 chi log q to the 2/3 double log q. And without this condition on where the characters live, the best you can do here is log q. Our bound has an implicit constant that depends on p, and it's something we can write down explicitly, but when q is equal to p, we don't win anything. But we do win if gamma is sufficiently large. Thank you.